Okay, so today what we're going to look at is actually finding the derivative of a natural log function. Before we get started though, I want to just practice a little bit more expanding and condensing logarithms. So take a moment here and try these on your own. Okay, hopefully you paused that and took a chance to look at this on your own, but let's actually solve these. If I want to expand this first one, ln of x minus 2 squared over square root of x squared plus 1, first thing that I see is I see some division. So when you see division, we can rewrite that as 2 natural logs, ln of x minus 2 quantity squared minus ln of x squared plus 1 square rooted, which I'm going to go ahead and write as to the 1/2 power. Okay, now I see I have some things raised to an exponent inside. I have the argument raised to the exponent, so that means that I can pull the exponent out in front. So I have 2 ln of x minus 2 minus 1/2 ln of x squared plus 1. Now, I cannot go any further because I have subtraction in here, and there's no rule for when you have a log of a difference, and also I have addition in here, and same thing, I can't take that apart. So that is fully expanded as you see it there. Alright, so let's go the other way. First of all, if I'm writing this logarithm as a single quantity, in other words, I want ln of something. The first thing I would do is I see I have a couple of coefficients, so I'm going to actually pull those in. I have ln of x plus ln of x squared plus 1 squared minus ln of, if that's to the 1/2 power, that means that's a square root of 2x cubed minus 1. Okay? Now I see addition and subtraction, which means that as I combine those logarithms together, whenever I see addition, I'm going to multiply, so it's x times x squared plus 1 squared, and where I see subtraction, I'm going to divide, so that's all going to be over the square root of 2x cubed minus 1. Okay? So these three logarithms can be condensed into the natural log of x times x squared plus 1 squared all over the square root of 2x cubed minus 1. Okay? So that's just a little bit of practice of stuff that we did back in pre-calculus. So at this point, we want to define what e is in terms of an integral. Okay. Now, as we look at this, you'll notice we're doing the integral from 1 to e of 1 over t dt, and that is the natural log of e. All right, the natural log of e, which equals 1. Okay. So now this is something we learned a long time ago. The natural log is a log base e, and the log base e of e equals 1. Here we're just defining it further in terms of an integral. Now one other thing I'll point out down here at the bottom is note that ln of e to any power, we can take that power with the same rules that we were just using and pull that power out in front, and ln of e is 1, so that just equals the power. So ln of e to a power is just whatever that power is. Okay? So let's apply that real quickly here. If I have ln of x and I have these different e's raised to different powers, we already said ln of e is 1 because that's e to the first power. Okay, and we're taking a log with a base of e, so those we've learned in the past are inverse relationships there. Okay, so This is actually pretty simple here. The ln of e squared is just going to be 2. Ln of e to the 0 is simply 0, okay, because that's 1, and ln of 1 is, or any log of 1, no matter what the base is going to equal 0. 1 over e is e to the negative 1, so ln of e to the negative 1 is negative 1. Ln of e to the negative 2 is negative 2, and ln of e to the negative 3 is negative 3. Okay? And then finally, just a little bit using our graphing calculator. Obviously, we have an ln button on the calculator, which is pretty simple. You could, if you wanted, though, to use the integral function on the calculator to figure out what these would equal using the integral of 1 over t dt. But we'll just do it with the function that we've got. So ln of 2 is going to be a 0.693. Remember, go to 3 decimal places. And by the way, also make sure that your answers make sense. You know that that e is approximately 2.718. All right, so 2 is less than 2.718. So I know that ln of 2 has to be less than 1. Okay, 2.7 is getting close to 3, and 3 cubed is 27, 3 to the 4th is 81. So if I'm doing ln of 32, I'm probably going to have an answer between 3 and 4, or at least around there. If I do ln of 32 on the calculator, I do get that. I get 3.466 if I round to 3 decimal places. 3.466. Okay, so pretty simple. And again, ln of 0.1, I already know that this should be a fraction. So ln of 0.1, and actually I know it's negative because it's a value less than 1 that I'm taking here. I know it should be negative, and it's actually a negative 2.303. Okay, so I misspoke. It's not that our natural log equals a fraction, it's that we're taking the natural log of a fraction that's less than 1, so we end up with a negative because you have to raise e to a negative exponent in order to get a fraction. Okay, so all of that brings us to what we really want to focus on today, which is the derivative of the natural log function. Okay, the derivative of the natural log function is 1 over x, and this is actually from that second fundamental theorem of calculus. If we look at what we did up above, we had the integral from 1 to x of 1 over, not equals, of 1 over t dt, and we said if that is e, then that's ln of e. Okay, if we make this x, then that's going to equal ln of x. All right, now if we take the derivative of both sides of this using the second fundamental theorem of calculus, we know that this right-hand side is just going to equal 1 over x. And over here, that is the derivative of ln of x. So that's where we get this from. Notice, though, we also do need to incorporate the domain. This is coming from a natural log. The domain of ln of x is x has to be greater than 0. All right, so don't forget about that. Even though you could plug in negative values into this, our original function that we were working with had this domain, so we got to stick with that. Okay? Now, where this can get a little bit tricky if you're not careful is when you have ln of another function. Okay? And it really shouldn't be tricky because we've done a lot of this kind of thing in the past just with different functions. If you have ln of a function, that means we have a composite function, which means we have to use the chain rule. So the derivative of the natural log of something is 1 over that something, but then you multiply by the derivative of that inner function. Okay? The easiest way I think to remember it is u prime over u. Okay, the derivative of the argument over the argument. Really easy way to remember that. So let's try a couple of examples of this here. Okay, so here we're taking the derivative of ln of 2x. Well, the inside function here is 2x. The derivative of 2x is 2, and I'm going to put that over the original argument. So it's 2 over 2x, which is 1 over x. Okay? Part B. Here's our inner function. Okay? The derivative of that inner function is 2x. So the derivative of ln of x squared plus 1 is 2x over x squared plus 1. And all of our other rules still apply as well. Okay, here we have not ln of a function, but we have ln of x times another function. So we have to use the product rule. Okay, just to recap here, u prime is going to be 1. Here v prime is 1 over x. So when we do the derivative, it's u prime times v. Okay. The derivative of the first times the second plus the first one times the derivative of the second. Okay? So that would be ln of x plus 1. Make sure to note that only the x is inside the ln. Alright, so there's our derivative using the product rule. Here, we do have the chain rule, but notice the function is not inside the natural log. The natural log is inside the function. Alright, so this is the inner function. The outer function is something cubed. Well, the derivative of something cubed is 3 times that something squared. And then I have to multiply by the derivative of the inside. The derivative of ln of x is 1 over x. So I could simplify this down to 3 times ln of x, quantity squared, over x. Here's a couple more examples, just for some extra practice here. If I'm finding f prime of x, again, using my rule, it's going to be the derivative of the argument over the argument. So the derivative of the square root is 1/2 x plus 1 to the negative 1/2 times the derivative of the inside, which is just 1, over the square root of x plus 1. Now this one's kind of interesting because I got this negative in my exponent, and that means I need to pull that down to the denominator. I can also pull the 2 from our 1/2 here down to the denominator, but I'm going to pull this down to the denominator. Well, that's the square root of x plus 1, and now it's going to be multiplied by the square root of x plus 1. So I've got the square root of x plus 1 squared, which is just 1 over 2 times x squared plus 1. The square root and the square cancel out. So there it turns out a little simpler. It can get even more complicated, all right? So here we have f of x equals ln of x times x squared plus 1 squared over the square root of 2x cubed minus 1. But I want to stop here a sec. Before we get things too complicated, we actually can make our lives a lot easier by remembering those rules that we've learned about logarithms in general. Where did we start out today? We started out with those expanding a logarithm into multiple logs. That's what I'm going to do right here. I'm going to make this ln of x plus ln of x squared plus 1 quantity squared minus ln of 2x cubed minus 1 to the 1/2. And actually I can go even further than this, make this ln of x plus 2 times ln of x squared plus 1 minus 1/2 ln of 2x cubed minus 1. You say, well, wait a sec, why don't we just go back here to the original and we can do the derivative of the argument over the argument? We could, but finding the derivative of this whole thing is going to require the quotient rule and the product rule with the chain rule inside of both of those, and it's really going to be a mess. Then we're going to have to divide by this whole thing as well. Okay? By simplifying the function itself, by expanding the logarithm, we can make life a lot easier on ourselves, because now when I take the derivative of ln of x is 1 over x plus 2 times the derivative of ln of x squared plus 1 is going to be the derivative of that, so 2x over x squared plus 1. Minus 1/2, the derivative of ln of 2x cubed plus minus 1 is the derivative of the inside, so that's a 6x squared over the 2x cubed minus 1. Okay? Simplifying a little bit here, I have 1 over x plus 4x over x squared plus 1 minus the 2 and the 6 cancel, 3x squared over 2x cubed minus 1. Okay? Now you may say, okay, well, what if we were finding max or min points and I had to set this equal to 0 and solve it? Well, at that point, you could get a common denominator, put it all together as one fraction, but even with that, it's going to be a whole lot easier than messing with that part. Okay? Now, just to prove my point, let's go back to part A and actually do it this way and show you that this would work, okay? So instead, I'm going to rewrite this as ln of x plus 1 to the 1/2. And that means that I could then pull out the 1/2, make it 1/2 ln of x plus 1. Okay? When I take the derivative then, f prime of x is going to be 1/2 times, what's the derivative of x plus 1? It's 1 over x plus 1. Okay? Well, you'll notice that's 1 over 2 times x plus 1. All right? And I just noticed I got a square in here somehow. Appeared. It should just be x plus 1. But notice here, once I get that, that's the same thing that I ended up with here. This method, we could say, actually is probably a little bit easier. Okay, because we didn't have to deal with the negative exponent, we didn't have to pull this down and combine those. All we did was that. So look out for that when you're doing the derivatives of these natural logs. You can make things simpler by simplifying the logarithm first and then taking the derivative. Okay, so let's apply this down here. And we have f of x is 4 minus x squared minus the ln of 1/2 x plus 1. Notice that ln, we can't simplify that logarithm at all. We're asked to find, though, the equation of the tangent at the point 0, 4. This is going way back to our classic application. What is the equation of the tangent line? So here for part A, we're going to find f prime of x first. Negative 2x minus, we need to do the derivative of the top, which is, or of the argument, which is just 1/2. That goes on the top, over 1/2 x plus 1 I need to plug in 0 to find out what the slope of the tangent line is. Okay, so that's f prime of 0, which is going to be 0 minus 1/2 over 1, or just a negative 1/2. So the tangent line that I have is going to be y minus 4 equals negative 1/2 x minus 0 using point slope form, and y equals a negative 1/2 x plus 4. Okay, now in part B we're told to graph f of x and the tangent. I've punched them into the calculator here. I hit graph. And in order to see that, I need to zoom this a little better. Okay, so let's go to zoom, standard. Okay, zoom standard. So obviously this is kind of a weird looking graph. But notice here, there we have the tangent. Okay. And we can see what we have. Now it says use the derivative feature to confirm your results. Okay, well let's see what they're talking about here. If I hit trace, here's I'm on my original function, okay, and I'm going to hit second calculate, and notice at the end here it's number 6 is the derivative. Now it's looking for a value of x. So since I wanted it at where at the point 0.04, I'm going to punch in 0 for x, and I hit enter. And notice it tells me the derivative was negative 1/2, just like we found. Okay, so we can do that. Another way that you can test this, if you come back here, I'm going to go ahead and graph. If I go to the math derivative 8, I'm going to differentiate with respect to x. I'm going to take the derivative of y1, and I'm going to make x equal 0. And when I graph that, you'll notice it's graphing a horizontal line because that's negative 1/2. If we then traced it, that would give us negative 1/2. Now it's kind of unnecessary to do this whole thing, but you can see it there. Okay? All right, so that is really it as far as talking about the derivative of the log function. We want to be careful, but also look for those opportunities to simplify before you differentiate. That makes life a whole lot easier. And at this point, what you can do is try some of the sample problems, the homework problems on page 329 for practice. Okay? All right.